Okay, so we're going to talk about encoders today. Now, encoders are something that are used when you have a DC motor. See, when you have a stepper motor, as you guys discovered in the last lab, you can make it step. You command it to step, and then it's there. As long as the torque requirements are not excessive, in other words, as long as the motor can turn, it will move to the position you command it. So it's frequent. In fact, I should go get a motor. I just thought of one more prop. Let me go grab it. So often what happens is a stepper motor is used without what's called feedback. So you have no way of measuring the position of the motor. Now, that's not always true. We actually have, let me get it out here. We actually have some stepper motors that have encoder feedback. Of course, you guys here in New Albany have probably already seen this. I'm bringing this motor out for the sake of the Anderson students. Anyway, this is a stepper motor. It has a lot of wires on it. The reason it has so many wires is because this section is for powering the coils on the motor. This set of wires is for the encoder feedback. So there's actually an encoder on the back end of this motor. Here's the output shaft. Here's the stepper motor. And then there's an encoder in here. Fortunately, one of these has been taken apart. I can show you what that back side looks like. So if we were to take the back off of this motor, here's what's on the back side, and it's pretty simple. It's just a wheel that has a bunch of holes in it. So you can see that there's several holes in the wheel, and there's actually a sensor in here. I'm trying to orient it so you can see it. In fact, the sensor may come out.
It does.
There we go. Yeah, nobody makes their own sensors into a housing like that. They'd buy it from someone. So this is a typical sensor. It's kind of like a photo switch. A photo switch is a little bit different. A photo switch is just a single detector. This definitely has two detectors in it. In fact, this one probably has two light sources in it. But anyway, what is this? Well, it's the same device that was used in the past in computer mice. If you turn over a modern computer mouse, you'll see a bright red light. Essentially what that light is doing is it's illuminating the surface that you've got the mouse on so that a camera inside can actually take a picture of the surface. And it takes, I think it's about 1,500 pictures every second that it takes. And it compares the pictures one to the next and computes the offset. So that's how modern mice work. It's actually the way that old mice on Sun Spark workstations functioned, except instead of having pictures, there was a special mouse pad that had a grid on it. And the camera was more simple and could detect motion. Anyway, we moved from that, of course, from the Sun station to what's called a ball mouse or a wheel mouse. And then, of course, today are the photo mice. But anyway, back at the ball mice, the way they worked, there was a ball that would roll, and the ball could roll, of course, any direction that you push your mouse, but that could be broken into two parts. You can't see it here, but there's actually a second shaft running this way with an encoder wheel here. Looks just like this one. You can see the shaft here, and you can see the encoder wheel. And as you roll the mouse forward and backward, usually the way this worked is your hand would be this way most of the times, because here you're clicking buttons. As you roll the mouse forward and backward, that would make this wheel roll. As you rolled it side to side, that would make this wheel roll, and any combination would be broken down into those two directions. Okay? So it's a simple mechanical system. And you might notice there's an encoder wheel here, as well as one here. And you can kind of see the individual slots in the encoder wheel. And you can actually see two different lamps. I don't know if these are the sensors or if they're the lamps. They're probably they look like the lamps to me. And you can see one of the sensors right here, this red or ruby colored thing. Basically, when there was a hole, the light would shine through and you'd get a light signal on this photosensitive transistor. Okay? There's another one under here. You can't see it because it's under the plastic housing that holds the ball. And of course, there are two over here as well. Now, this is a really old style mouse. The more modern ball mice actually incorporated the sensor and receiver into one package and had both of them on one side of the wheel. You can actually do that too. Okay? And I'll show you how that works here in just a second. But let's look at the details of how this phototransistor and lamp work electrically. Essentially, you have a voltage source. That voltage source, as we've already connected before, goes through a resistor to a light emitting diode in the back to ground. So this basically turns on a light. And so that's the way the mouse worked, is it had a light. It actually had two of them, but on each axis. But just imagine one light that's on all the time. Now, the photosensitive transistor is just like a switch that when you shine light on its base, instead of putting electrons on its base or a charge on its base, it will conduct. So think of this as a switch, and when light shines on that switch, it conducts. When light does not shine on that switch, when it's blocked, it does not conduct, it opens up. Okay, that's basically how phototransistors work, or how we need to think of them. So basically this is like a resistance or a voltage divider, right, with two resistances, where one resistance can be a high resistance or a low resistance. And so what happens is, when there's nothing blocking the light from the LED, it'll shine on the base of the transistor's on, and the output will be tied close to ground. But when you block the light by putting something in between the LED and the phototransistor, what will happen is this will be high resistance, and this pull-up resistor will pull the output up to high voltage, right? So think about it. Essentially what you've got is a light, I'm trying to make an encoder with my hands. You have a light and a detector pair, and then you have the encoder wheel going by, where either it can see light or it can't, or so on and so forth. So you can actually count on-off transitions and count how many ticks have gone by, and therefore figure out how much motion has occurred. Now, like I said, you don't have to do it that way. This is an older printer that has a stepper motor on it. We know it's a stepper because if you look at the stepper motor that drives the carriage, it's a 4-wire motor. There's no way that's a DC motor. And if you look in here, you'll notice there is no encoder. Okay, so as you move the carriage back and forth, there's no sensing element to sense the location of the carriage, because you simply count how many steps you command the carriage to move, and you know the position of the head. That's an old printer, and you can tell it's old by looking at the circuitry. There's a lot of surface mount devices, but the components are larger than they are today. This kind of chip, a dual inline pin chip, is becoming more and more rare because they take up a lot of space. Anyway, there's one more thing though that this has that's similar to what we're talking about. It has a lot of flags or photo switches. There's a flag here that trips a photo switch. You can kind of see it in there, and it's basically a single detector and you could call it a sender receiver pair if you want. Basically a light and a photosensitive transistor. There's another one here that's a lot smaller, and that's all I see on this circuit. There may be another one somewhere else, but for now that's all I see. Anyway, they're closely related to what we're talking about, but what we're talking about is a little more complicated. It has two sensors, not just one. Okay? And you'll see why we need two here in just a minute. Excuse me. Here's a bit more modern printer. This one, you'll notice the circuitry is much smaller on this board, more integration of components, and the typical logic chip is much smaller. It's right here. I'll see if I can point it out on the camera. That's equivalent to one of those dual inline pin circuits. There's a mechanical switch on this, so there's a switch that's activated here. Well, maybe it's mechanical. I can't tell for sure whether it's optical or mechanical, but there's certainly an optical switch down here. Let's see if I can, and I'll pass this around for you guys in New Albany here in just a moment, but right here is a flag, and let's see, there we go. There's a flag, and there's a real small sensor here. So let me pass it around. Just point out where that flag and sensor are as you go around. So like I said, those are a little more simple. Now the thing about that I forgot to show you is that the carriage is moved back and forth by a DC motor instead of a stepper motor. And so you need position feedback. So there's actually an encoder strip that runs along the length of the carriage axis. And as the carriage goes by, it actually has a couple of sensors that can sense and count how many strips have gone by. I don't need that one back. I can show you guys on this one. This one's even easier to see. This is an even more modern, this was actually a printer and scanner combination. And this one is really easy to see. There's an encoder strip right here, and if you probably can't see it on the camera, but if you look at it really close, you could see individual lines running this way on the encoder strip. And this one's pretty easy to see. Right back here on the circuit board, there is a sensor that wraps around the encoder strip, and as it moves up and down, it can count the number of lines that have gone by. How do I know this one's more modern? Well, they're using a DC motor for the carriage axis, and they're using a DC motor for driving the paper feed. And you'll notice here there's a wheel, and that wheel, you may not be able to see it on the video, but it has individual lines going this way, running radially. And the sensor's not here. The sensor was built into the base. There's a circuit board somewhere that has another sensor, encoder sensor, that wraps around it. So if you want to pass it around, you can. If you've already seen all this, it's fine. So I'll pass this one around as well. We'll start this one this way. The main thing to see is the sensor for the encoder on the back side of the carriage. So just point that out as you go. So this is a lot like the old ball mouse that we used to use. Now, of course, each axis has two of these. It has, usually there's two lamps, so it doesn't have to be, and there are definitely two transistors. And let me explain why. If you think about it, that strip, whether it's a linear strip or a rotational strip, an encoder, if you're just counting the number of lines that go by, you can't tell anything about the direction, right? All you can tell is that we've had a transition from high to low or low to high. So how could we use an encoder in order to detect the direction? Well, there's a pretty clever idea. What if you offset each detector just a little bit from the other? And let me get a simpler view of this. Here we go, this is good. So here's our encoder strip, and here's light detector A and light detector B. Okay, in fact, for the sake of the students in Anderson, I'm going to zoom in just a little bit. I'll try to put all this into a nice presentation and post it for you guys, but in the meantime, hopefully you can understand from this discussion. So here's our encoder strip that has light and dark, or on and off, on, off segments. So as the strip moves by the detectors, detector A, for example, right now is sensing light, right? So here's detector A, it's sensing positive 5 volts or high, whereas detector B is in a dark strip. So it's detecting an off at this time. Okay, that would be down here. As we move the encoder, notice what's going to happen. B is going to change before A does, because B is going to end up in the true area, right, where it gets, where it senses light, while A is still in the true area. So both are going to be high or true. Now think about it. If we went the opposite direction, what would happen? If we didn't go this way, if we went this way, what would happen? Well, B would remain dark and A would go dark first. So by detecting which one goes dark first or light first, whether it's A or B, you can tell which direction the motor's moving. Okay, so this is called quadrature, or encoder quadrature. And the, go back a bit. I really like the animated GIF because once you wrap your head around it, it makes a lot of sense. So you can actually see two sensors, okay? Sensor A, sensor B, sensing either a false or a true. True would be where it can see light through the encoder wheel. You can see the encoder wheel moving around. And you notice that sensor A is leading sensor B. In other words, sensor A changes to something and sensor B follows afterward. If it was rotating the opposite direction, B would lead A. Okay, so by noting which changes first and which one follows, in other words, which becomes the same as the other one was already, then you can tell which direction it's going. Okay? Now notice that there are 4 possible combinations here, and all combinations are used. Okay? Basically what's happening here is this encoder wheel is counting in gray code. So you start off with 0, 0, 0, 1, 1, 1, 1, 0. In other words, there's only, let me draw it on the, well, if I draw it on the board, here, I know what we can do. Gray code, images. Yeah, this is gray code. So essentially what happens is, let's see, can we see it on the screen? Maybe not. Let's zoom in. Okay, so there's many different flavors of gray code, but we're interested in this right here where we have 2 bits. The rule with gray code is that you cannot have 2 changes in a line. In other words, we've got a 0, 0. What changes? Only this bit changes. Now we can't go to 1, 0. If we went to 1, 0, then this bit would change to a 0, this bit would change to a 1. That would be 2 changes in one line. In gray code, that's not allowed. So instead what happens is we flip this bit to a 1, and now we can flip this bit back to a 0 to get all the possible combinations. That's exactly how an encoder works. It gives you this gray code counting, and if you think about it, this order 0, 0, 0, 1, 1, 1, 1, 0 is the opposite order to 0, 0, 1, 0, 1, 1, 0, 1. See how I went the other way? And so you can tell from the encoder which direction the motor's actually moving by using quadrature. That's why each of these, the mouse, for example, that I showed you, or these sensors that I've shown you that are on the encoders, they all have at least 2 detectors on them. Okay. Now, the Anderson group took apart printers, and they were asking about the encoder and trying to figure out where all these things were. I talked to them a little bit about it during the printer and microwave teardown. And they showed me the back of their circuit, and I was able to tell which were the lamps and which were the detectors, and I can help you guys do the same. But what we need to do is we need to reverse engineer these sensors, so the sensors that are on the encoders. And one way you can do it is pretty easy. You can take the circuit off, because there's screws and things where you can disconnect it. And I guarantee you that whoever made Hewlett-Packard, I guarantee you Hewlett-Packard did not make that detector, okay? If you can look at that detector and get a number off of it, you can look up a data sheet and find out. On the other hand, if you take the circuit board off and look at the back of it, you can actually tell usually by the traces which is the detector and which is the lamp. Okay, so I can help you do that. So we need to do this. I think there's one group still that has to finish off the stepper motor lab, right? Or are you guys done with it?
We're done. I just need to explain everything how they did. Yeah.
Okay, all right, perfect. So we're ready to do this today. Here's what we're going to do. We're actually now no longer calling these labs. Now we're calling this the project. But the project is broken down into multiple parts. The first thing to do is to get an encoder to count and tell you which direction you're moving. Does that make sense? So what I want you guys to do is to make it so that you can move this carriage back and forth manually and have it connected to the Arduino, where the Arduino counts up and then counts down. Does that make sense? So we're at position 0, we're at position 100 because 100 lines have gone by. We're at position, I don't know, say 1,000, I don't know how many there actually are. Okay, and if I move down, we're at position 800, 500, and it just keeps track of where it's at. That's our first step, because in order to use the DC motor, which, where is it on this? Here it is. In order to use this 2-wire DC motor, we're not commanding positions, we're just saying go. Well, we have to have some kind of feedback to know where the carriage is located if we want to use it. So that's what we're going to do first, is get the encoders to work. And then what we'll do is we'll pause on the encoders, and I'll tell you how to drive a DC motor, because with a DC motor, you don't just want on-off, you want a speed, right? So how do you do that? Well, you use something called pulse width modulation, but I'll explain that next time. You've got enough information to work on these encoders and getting those working. But we'll use pulse width modulation, and we'll be able to change the speed as well as the direction of the motor. And then finally, we'll wrap around all that with a PID loop, a control loop, which I'll explain more later as well. And then on top of the PID loop, we'll build some path planning to actually get the thing to move the way we want it to move, okay? So, but your first goal is simply to get this to count where you're at. That's all you really want. Okay? Now, if you think about it, you'll realize these are relative encoders. They're actually absolute encoders as well. Let me show you what an absolute encoder looks like. Here's an absolute encoder. And you can tell it's absolute because, look, there are actually 3 different rings here. So there are 3 different detectors here. And each position has a unique code. Right? So we've got any white space would be on, any black space would be off. Yeah, that's the way they're doing it. So there's what? We got 3 bits. So how many different locations are there on this wheel? 3 bits.
9.
It would be 8, right? So there's 8 different possible combinations, 2 to the 3rd power. So if you count how many there are 8 different positions. Well, that's not very good resolution, right? I mean, you can measure the motor's position, but only within an angle of whatever 360 over 8 is. I can't think right now. Okay. But that's a pretty wide angle, right? The motor could be anywhere in that region, and it would still give you the same position feedback. But what's interesting about this is that it is an absolute encoder. You don't have to home this axis. In other words, wherever the encoder is at, you can tell its position. It's got a unique signature for each position. Now, I said you don't have to home it. In reality, what I mean by that, most robots use encoders that are relative encoders. In other words, it's just a bunch of lines on a disk or on a strip or whatever. And so when you turn on the robot, what it has to do is it has to go to a known position. Usually it'll have switches on the inside of it so that when it reaches a particular position, that switch will be tripped, and that's its zero. That's where it knows to begin zero. You're going to have a similar problem with this, right? Because if your carriage starts here, your count has no reason to start at, let's say it's in the center, your count has no reason to start at 500 out of 1,000, right? So you have to start at a known position, either this position or this position, and frequently there are switches on these, and I'm looking for it in this case. A lot of times it's a photo switch, but I don't see it on this one. A strategy that was employed for a while, I guess it still is, that feels like something there. Yeah, there we go. There's something mechanically moving down here. I imagine it probably triggered a switch. But if not, one of the strategies, my mother, when she was alive, had a printer. She was an artist, and once she discovered that she could do all sorts of art on the computer, she was hooked. She's actually a really good calligrapher, but she started doing a lot of work on the computer and using all kinds of fonts and things. Anyway, she had this printer, and what it would do is when you turn it on, you'd hear it go over and make this loud noise. That's because it's homing. What it's doing is it's saying, just turn the motor on for a certain amount of time. Even if it's over here, it'll move all the way to that position. If it's here, it'll just move over here and skip mechanically, and now we know where we're at. Okay, so that's one method of homing. It's pretty crude, but of course inkjet printers are pretty cheap, so who cares? A lot of them do use a flag because that noise obviously bothers consumers, right? They think something's wrong with their printer, when really it's just an engineer's cheap way of getting around including an extra switch. So anyway, hopefully you understand the problem with absolute encoders is you need a whole lot of sensors to get reasonable resolution. And another problem is even with an absolute encoder, if this is an encoder on the back of the motor, but the motor's geared down so that the axis can move a decent distance, well, you still don't know what your position is with an absolute encoder, right? Because the pattern is going to repeat as the axis moves. Does that make any sense? Okay, so the pattern will repeat multiple times, and so it's still a relative type of encoder. But this is a simple illustration of what's called an absolute encoder. Real absolute encoders typically have at least 8 sensors, and that's a pretty low resolution. And I don't mean 8 combinations like this, I mean 8 bits, so 256 different possible positions. Okay, any questions on encoders, how they work, and what we're trying to do? I wish I had the back of that circuit board, the picture that Anderson sent me. Let's see, let me try something quickly. I wondered if I could find an image where someone's showing the back side of a circuit where we can interpret it. If we could see this board, we could do it, because there are 2 resistors here. This is an older one, but I don't see what I need there. This is what the sensor and light pair look like. This would be the light. Well, actually this has 3 leads. This one may be a little different. Usually the sensors are dark and you can't see inside of them, and usually the lights are clear and you can see through them. I don't see the circuit I'm looking for. If I find a circuit board like I'm looking for, I'll show you guys. Here's a very simple encoder. This one's pretty crude. You can see that you've got 1, 2 light areas and 2 dark areas. I don't think this one would work very well because you can see the 2 sensor pairs here, and the spacing of the 2 sensors depends on the distance between the light and dark areas. It looks like the light and dark areas are much too far apart for the spacing in quadrature to work. But anyway, let's see. Well, I don't see what I'm looking for. I'll see if I can find it, because I've already described this to the Anderson students, so there's no need to have this on the video. But I'll try to find the picture that they sent me. I'll go to WebEx and see if it's still there, and then I'll show you guys and show you how to interpret the schematic. And of course, if you need help as you take apart your carcasses here and start to figure out, or try to figure out what's going on with the sensors, I'll help you figure it out. Questions, comments? All right, that's what we're doing today.